Okay, hey folks, and welcome to Iron Middle, a show where where the last two episodes we start without seeing me, and this time camera works, but it's not that camera which I usually use. So let me try to sort this out. Actually, no, let's not waste time. Forgive me my angle. So yeah, Iron Middle, a show where we look at the target middle database and try to understand how this thing works and how you could build a similar database yourself. And this is kind of like fascinating. You know, like we could watch a talk about target middle, or there is a pretty thorough architecture.md document in the repository, or you could just think from first principles, how would you build this database? And that would be much faster. But this present series, which is, I think this is episode number 70, so the previous episode was number 70 minus 1, it's like really deep dive, really low level into everything. So, okay, what are we going to do today? We continue our big arc of studying the vopr, view stamp replication operation replicator, which is a name from some obscure movie which I haven't watched yet. So the idea behind the vopr is simple. We take our physical system, which is comprised of 6 replicas running on different machines, connected via network and connected to a bunch of clients. And instead of trying to run this full distributed system physically, we run it logically. We explicitly say that, hey, every replica and every client is a state machine. And those state machines live in the same timeline. And they all process incoming events one by one. So we fully capture disk I/O, we fully capture network, we even inject failures in our captured input-output, and that allows us to run the entire system on a single thread even. Not even multiple threads in a single process, really single thread, really like very explicit state machine stepping. Crucially, one of the things we virtualized in addition to storage and network is also time. So not only you don't need to rent 6 machines from Amazon to run the simulator, you also run it 100 times, 1,000 times, I don't actually know, like many orders of magnitude faster than if you were running it in real time. So I think we've looked at the vopr in general, like the structure, how to run it, how to parse its output. We've looked at how this event queue works, how we schedule asynchronous operation, how we use fake storage. And the last time we looked at how we inject faults, how we can corrupt messages of the network, how we can replay messages or drop messages, how can we corrupt data in the storage, that sort of stuff. So today I want to do the opposite of that and to focus on how we solve correctness. So let's say we've run our state machine through vopr on a particular sequence of events. How we know that the results are correct? How we know that the state machine is not buggy? And here, well, I mean, if you look at the system as a black box, the way you solve it is through some kind of a search. So usually a distributed system gives you a guarantee like this. A bunch of operations is submitted to the system, and the system behaves as if all those events, all those requests were processed in one specific order, but that order is kind of arbitrary. So the way you test this kind of system is that you take incoming events, you specify like certain constraints, like for example, if your system says that, hey, kind of like if you do this and then that, then A happens after B, then you like encode constraint that A happens after B. And then you search effectively through all the permutations of all the events to try to find the permutation which corresponds to what your system is doing. This is not what we are doing at Target. At Target, we have much simpler solution. Let me show it. So, no, I don't know. I don't want work. I don't want KMP. I want iron middle. If we open our data model, let's say transfer, we see that there is a timestamp in the transfer. So the reason why we can have a timestamp is because Target promises two things. First of all, it promises strict serializability. Not only there is some sequence of events, that sequence of events actually is going to be consistent with real life ordering of events. So if I send a transfer to you, receive a confirmation that I've sent you a transfer, and then I phone you and say, hey, I've sent the transfer, you can check it that it is there, and at that point you go and check the target bundle, you will see the transfer. Like, you know, there is like very strong consistency guarantees. And second, not only we say that we have this guarantee, we actually go and explicitly expose this by assigning a unique monotonic timestamp for every event. So no two transfers can be created at the same time. Every two transfers, like the timestamp will be different. They might differ by just a single nanosecond if those two transfers end up in the same batch, but they will be different. And this and then you can use the timestamps to actually find out the order in which events occur. So you don't need to search. The database actually gets you this order of events. So that is kind of like what are we, that is like our plan for checking correctness. First of all, we want to check like internal consistency, that there is no assertions that all the replicas ended up in the same state. But then we actually want to check this very strong consistency guarantees that the results are the same as if we executed all of the transfers in the order of their timestamps. So, okay. Let's see how that works. And let's start with our main loop. So, it has two parts, the so-called safety mode and the so-called liveness mode. The job of a safety mode is to process all the given requests. So when we run the simulator, we we generate a certain amount of requests we want to funnel for the cluster, and then we tick this safety part of the simulator until we have received replies to every request. Then we tick the so-called liveness mode. So when you processed all the requests, that means that for every request, some replica processed it. And it also means actually that the latest primary processed all of the requests. But there is no guarantee that every replica processed every request. So some replicas might be falling behind. So in this liveness mode, what we do is that we check that not only the clients received their replies, but also that all the replicas converged to the same state. Okay. So how does it work? Oh, no, that's actually not the liveness mode. So this is else to our safety mode. So we try to process all requests, and that didn't work. So if that didn't work, it might still be correct that it didn't work if what happened, for example, if we had more faults than our fault model is allowed. But yeah, so this is liveness mode. And this is our first check of correctness, check of convergence of all the replicas. So let's see, what do we do here? Well, first of all, we see that all requests were answered, pretty reasonable for convergence. Then Okay, I feel like I need to explain a little bit more about this liveness mode and this concept of core. So the soft core version of liveness mode is that you just wait until all replicas converge, while otherwise running the cluster normally. But the problem with that is that it might miss some of the errors, because while the cluster runs normally, it also crashes and restarts replicas periodically. And as you all know, just rebooting the computer is often a good way to fix a particular problem. So it might be the case that replica is stuck in some bad state, and it will get out of the state if we reboot it. And because our simulator does reboot replicas periodically, we'll actually miss that thing. So what liveness mode does is that it freezes the crashes in time. So the crashed replicas remain crashed. The uncrashed replicas remain uncrashed. And we need to check that even in this situation, even without injecting any kind of extra reboots, the cluster is still able to converge to the desired state. And this is the idea of a core. Like obviously, like if every replica is down when you start the liveness mode, you cannot converge because everyone's down. So what we do is that we select a subset of replicas, which is called core, and we make sure that those replicas are up and those replicas can talk to each other. Other replicas can be down. And we check that the core converges. But well, if a replica is down, it obviously doesn't have to converge. Okay, so first we check that all the replicas are on the latest release. And that means that I actually need to explain releases. Let me see, do we have... Okay, we don't have upgrades. Well, actually, okay, I think we can cross out liveness mode because I've just... well, no, we do have upgrades here. Let me add some more exclamation marks so that we don't miss it. Yeah, and liveness mode we just described. Okay. Then we check replica convergence. Let's see. So what do we do here? We say that commit mean for the replica. So the op which was actually executed on that replica, as a reminder, commit mean is what the replica executed, commit max is what's executed on the cluster. So okay, we check that for each replica, its commit mean is the same as the largest op which was ever committed by the cluster. Now back button is broken again. Replica convergence. Okay, yeah, that's it. Then we check cluster convergence, which is to say that yeah. So we know that all the replicas are on the same commit mean, and we know that obviously, like if everyone is on the same commit mean, then this commit mean corresponds to the cluster's commit max. And then we check that what we have fully hash chains. So yeah, like just chains has the correct op. Why the back button doesn't work? Back. This is infuriating. Okay. Convergence. Okay, yeah. Then we should check that. So far, we were talking about the log. So we know that kind of like all the replica acknowledged every single prepare that it needed to acknowledge. We still need to check the state. So the first part to check in the state is to check that there is no state sync in progress. So we actually, that each replica actually has the prepare, and that each replica synced all the tables. And then we check that the checkpoint of each replica is the same. And yeah, if that's all right, we return null, which means that there is no phase which is pending. So here we checked clusters self-consistency. We know that everyone is on the same page. We don't quite know that this is the page we are looking for. So there's still kind of, the possibility that the state is self-consistent, but is still wrong. I'm wondering, where should we start looking at this? Well, let's maybe start with more checkers. Let me see. So there is one very scary thing which is called auditor and workload, and those probably will cover, I think, in a separate episode because they are like hellishly complicated. So today, let me focus on other checkers we have. So we have cluster, and in the cluster, we have a bunch of checkers, which kind of like still do this like self-consistency things. So let's see what they do. And let's start with state checker. So I think, and again, like this is parts of the code which I'm kind of like relatively less familiar with, so bear with me. But I think what state checker does is that it checks the logical state of a cluster. So it observes the messages that the cluster emits and reconstructs the internal state from those messages. And then, we use that to check consistency. For example, this is the thing which maintains commit numbers for each replica. Okay, let's see what we do here. So we do some initialization, where we do something with commits. What is commits? So commits is just an array list of prepares which were committed with information about who committed them. So yeah, and we start with the root prepare, which is committed by everything. And then we have client replies, they need. Okay, let's quickly double check that our dnit here is working correctly, because well, Zik won't check this for you, so you need to do this yourself. And the good way to check this is usually like pair deferrers in the init and stuff in the init. So we initialized commit and we deinitialized commit. Okay, that is reasonable. Okay, this is reasonable. So then we have client replies, replica head max, replica head max. Okay, yeah, that sounds correct to me. Okay, yeah, that's I mean, this is like the kind of code which is like super easy to get wrong, and honestly, I'm kind of like unsure how people who write Zeek and allocate liberally manage to not do this kind of errors. But for TinyBittle, we generally just don't ever call dneeds, and we call each init exactly once at the startup. So we probably do have a bunch of bugs in our dneeds, but we just don't care because there isn't a normal way to shut down the TinyBittle binary. It's always just Control C, kill the entire process. Okay. So I guess the most interesting method is here, like this like state checker on message, which kind of like observes the messages created by the cluster and infers what state the cluster is in. So for example, you see, when a prepare OK message is emitted, the state checker records that the latest commit that the replica knew about was like something that it okayed. So, and then when we periodically call check state for the replica, we actually check that it never regresses its head max. So basically, the bug here would be if a replica at some point says, hey, I've heard about prepare number 92. And this is like the largest prepare I've heard about. So I've never heard about prepare number 93. And then this replica crashes. And then this replica restarts and restores its state incorrectly, such that it now claims that it only saw prepare number 90 and haven't heard about prepares above it. If a replica were to do so, then the state checker would say, hey, actually no, your current op is lower than the op you previously acknowledged. So you must be in error. And let's quickly check where we call state checker. So yeah, we call this. Well, do we actually check this? Oh yeah. So we basically call this on every tick. So if at any point in time a replica reneges on its promise of op, we call it and say, hey, actually this is not good. Please don't do this, because this is the contract or the sending of a prepare OK message. If you are sending a prepare OK, you guarantee that you will never ever forget about that particular message, that it is safely stored on your durable storage. And taking the storage fault model into account, even if that message gets corrupted on disk, you will at least claim that, hey, I have corruption and I don't know what I have. But you will never ever positively claim that you do not know a larger message. Okay. This is it. So, and then we also record replies. I wonder I wonder why we are using replies. Where like in that code on message we record client replies, but where are we using this? We aren't using this really. How could it be? Well, maybe something else is using client replies. So this is checker client replies. Okay, yeah. Oh, okay. Yeah, that's interesting. So, well, I guess, I mean, I've crossed out the liveness mode, so I might as well explain it fully. So, what is the problem? The problem is that everything fails all the time. Well, I mean, real life is not actually Murphy's law life. Most of the time, things work correctly. But in the context of Tiger Beetle's vopr, it's its job to make everything fail all the time. So yeah, the amount of failures we have is gigantic. But our fault model admits only a limited number of fails. So yes, we do tolerate disk errors. But if you start all the 6 replicas and point every replica to TMPFS to, like, disk, quote, quote, disk, backed by random access memory, by volatile memory, rather than, like, something which survives a crash, a power loss, then obviously, like, you don't get durability guarantees. So I think what we guarantee is that if for every sector on disk, if that sector, well, sector is not correct, like for every like chunk of data. So like a grid block, a reply, a write-ahead log entry. So if for every record on disk, there is a replica in a cluster where this record is not corrupted, then we remain available. We repair that. And it is actually horribly painful to ensure that you do not inject too many corruptions. It actually is hard to get to a situation where like you guarantee that you do not by accident corrupt a particular grid block on every replica, while at the same time injecting a sufficient number of failures. So we actually kind of like, we tried originally to not inject too many faults, but we backpedaled from that approach for 2 reasons. For 3 reasons. Reason number 1 is that it's just very hard to control how you inject the faults. So like if you open fault atlas, where is fault atlas? Such a beautiful name, but not really a great idea, sadly. Sadly, this data structure needs to go. So if you open like fault atlas, that's like a bunch of lines to figure out what you can and cannot corrupt. So that's kind of like the first reason why trying to inject not too many faults is hard. Like it's just hard code to try. The second is that you will necessarily over approximate this. So ideally, you would want to inject almost to the limit number of faults. You want to inject like a limit number of faults minus 1. But because like the code is tricky to write, what you end up doing is actually injecting like rather conservative number of faults, like 1 or 2 or 3 faults there. Like you don't do like, hey, we like corrupt almost everything. So we like you do want to inject more faults. And the third thing, is that even if there is more disk corruption than we agree, even if a particular block is corrupted everywhere, what we actually want to do is that we want to remain correctly unavailable. We do not want to silently forget that we had data. So kind of like, we can be like fully available, fully correct if we have few faults. If we have too many faults, we just remain unavailable. But we will never flip to available back again unless you like literally erase the entire data sets on all of the clusters replicas. So in other words, it is correct for us to inject too many faults and check only correctness guarantees, not liveness guarantees. So coming back to client replies. Well, actually, okay, let me quickly check one thing. I think I realize why my back button isn't working, and I fear that what is navigate backward? Go back. Well, it should be working. So I was thinking that maybe I have changed the button to do this on a single file, but no. Okay, it's just broken. Well, anyway, so bottom line is that yes, we can inject too many faults, and we need to figure out if we are unavailable. Is it due to us injecting too many faults, or is it due to us having a bug in our code? And this family of fan core missing functions, core missing primary, core missing quorum, core missing prepare, core missing blocks, core missing reply is actually what checks this having too many faults condition. So here, one of the convergence criteria for us is that each replica remembers reply for every client which has an open session with the cluster. But it could be the case that a reply is corrupted everywhere, and we need to check this. So we check that for every client reply, we check that someone in core knows it. And if someone in core knows this reply, then everyone in core should know this reply. If no one in core knows this reply, then this likely means that we are correctly unavailable. Okay, so let's go back to our state checker. Okay, so this was this is like the two bits of state that we track from messages. The prepare case, which we use to check that the replicas do not regress on the head up, and to check that at the end everyone is on the same page, and replies, which we use to check that the core correctly has all the replies unless everyone in the core is missing reply. So this, okay, I think this is confusing, so let me kind of like repeat this. With too many faults, there might be like two scenarios. Either every replica in the core, in that subset of replicas which we make available in the liveness mode, either every replica in the core knows a particular fragment of information, like the reply, or no one in core knows about it. Both of those cases are fine. The first one means that, well, the replicas are in sync. The second one means that we have too many faults in the core. What would be incorrect is that if some subset of a core knows this information, but some replica in the core doesn't, that means that our repair isn't working. Okay, so let's see Okay, yeah, and replica convergence, classic convergence, we actually already seen before. So let's see what do we have in the check state function. Okay, so again, this is something which we call onTick. So for a replica, all the time we check its consistency. Okay. Ha. So yeah, apparently, state sync might regress our commit a little bit, which is like, okay, yeah, that makes sense. So if the replica is not in the recovering head, then we check that it does not regress on its head max promise. And recovering head is exactly that. Recovering head is a state where you do not know what is the latest op you have acknowledged. So you need to talk to the primary to understand what is the current latest op. Okay. Then header A, what is header B? Checksum B. How do we? Okay, so I think the check we are looking right here is to check that we never that no two replicas try to commit different ops at the same op number, so that they always commit the same, which kind of like we check redundantly at the end. Remember, we check that, well, actually no, that's not redundant. So at the end, we check that everyone agrees. But that is not enough, because potential failure here is that at some point, someone disagrees, says, hey, no, actually, there is a different top committed here, but then kind of like repairs this and backtracks. So the fact that at the end of a test, you observe that the state of the replicas is the same is not enough. You need to check that at every point on the path there is also what's consistency. So here is what we do here. Okay, so we take op number from commit mean, the previous commit mean we knew, and then the new commit mean. We take the actual header and we take the checksum. So I think it goes checksum A, checksum B. I feel like somewhere here we should be looking at the parent. Okay, yeah. So indeed we check that. So yeah, so basically we observed that we have advanced replicas. Oh wait, no. What is commit A, commit B? So commits. Okay, yeah, they are both replica local commits. Okay, so basically here we observe replica advancing its commit. So previously we knew that it committed up to op number 91, and now we see that it committed op number 92. So we need to check two things. First of all, that ops number 91 and 92 connect through the hash chaining, and then we need to check that everyone else who commits op number 92 commits the same checksum on the commit number 92. So yeah. If the replica local commit is less than the cluster commits, then we say that the replica did commit this commit. Somewhere we should be ascertain okay, it's here. I don't see where do we check that this is the same commit. I'm not seeing this. Well, okay, I don't want to hang up on this for too long. So basically, this is the branch where where someone was before that, and we just say, okay, now we are at this state again. Otherwise, we are advancing this and say, hey, we have a new commit. We have, yeah, we have a new commit. Yeah, okay. I'm still confused that we are not comparing the checksums here. Okay, let me find this because this should be so. Header B is replicas checksum. So we should. Is it this thing? So checksum A. Okay, yeah, this is it. So checksum A is a checksum from the cluster, and header B is a header from the replica. And here we, well, no, it's not it. It's header B checksum, header B checksum. Yeah. Okay. Okay. So sorry. I want to skip it, but I kind of like feel peculiar. Okay. Let's try to read this carefully because I mean I'm bugged that I'm not seeing comparison of the checksums. So okay, let's read it line by line. So commit A is commit for this replica, like the latest commit mean we saw. Commit B is what we are seeing right now. Okay, and header B is what we have. Okay, so we expect. Okay, so actually, I hate this because this is, it's much more readable if it would written this way. If header B is null, then we know that replica is at the checkpoint, which makes sense. If replica says that it commits something, but it doesn't have the header, the only way it could be is that it is actually at the checkpoint. And then, again, if header B is not null, then it is like the same applet it should be. Okay. So now checksum A is the checksum of the previous commit marks of the replica. Okay, checksum B is the checksum of the current commit. Okay. If those are the same, so if we haven't advanced, then the checksum match. And if the checksum match, we don't do anything. Okay, that makes sense. Then we say, okay, so now actually we advance our commit A. Okay, so how could it be that commit B is less than commit A? Well, I think this is kind of like this. This should be this case. Or maybe I'm mistaken. Okay, so anyway, we say that like right now our commit mean is commit B. Then we check the commit which we should have, and then we assert that commit, but we don't actually. Okay, assert commit header checksum equals header B checksum. Like this should be here. I don't understand why we don't do this. Okay. Okay. Then I'm confused. I don't think we kind of like actually assert this, and it feels like we should be asserting it. But anyway, so the main thing we do here is that we track which ops are asserted, because what do we insert? Like we insert header B. Well, yeah, like we definitely should be checking that this header B is the same as the one before. Okay, and I think that's actually maybe all for state checker. Well, okay, we have a few minutes left, so rather than jump into some other checker, let's actually do something productive. Let's write this as a pull request. State checker checks. So I want to make the code larger. Well, wait. That's too large. Okay, state checker. What did I want to do? So I want to say that if header B is null, we assert that we are at the checkpoint, and if it is not equal to null, we assert that it is the same commit. And here we assert if header B assert commit header checksum here be I think we want checksum. So checksum. I think this is what we want. Let's see whether this is compiled, and while this is compiling, let's say vopr assert that replicas agree on commits. State checker tracks the sequence of commits made logically by the cluster, but unless logically by the cluster by observing individuals replicas commits and advancing the watermark, unless I am mistaken. If the watermark is not advanced, that is a different replica committed first. We don't check that we commit the scene prepare. This feels like an oversight. Okay, so let's see. Let's kick our local CI. Oh, by the way, what's okay? Yeah, our quick check passed. We want to label this with vopr. And when our CI passes, we should assign this to Chaitanya. Interesting thing. On GitHub, you have reviews and assignees. How do you pronounce it? Assignees. We don't use reviews because reviews are level triggered. Like, you request a review and then you do a review, like the status that you need to do a review, it is cleared. Rather, we kind of like want to make this sticky. And until this pull request gets in, it will be both on me and on Chaitanya to actually see it through. Like that way, like there is no possibility that the pull request gets dropped on the floor, slips through the cracks. While you are assigned to it, you are responsible for getting it in. So, okay, yeah. We've merged it, and I think we could maybe wrap it up today. So, okay, we haven't done everything I wanted to do because I actually wanted to cover like the entire correctness checks of vopr. But on that hand, we covered liveness mode. So that's actually good progress. So to summarize, we've started looking at how we check correctness. And we've looked at 3 specific checks. First, we looked at how at the end of a cluster, at the end of a vopr run, we check that the state is consistent, that every replica is on the same page. Then we looked at the liveness check modes. We noted that it might not be true that all the replicas are on the same page if our testing hardness injected too many errors. So we have those checks which says, hey, if the replicas have too many failures, then it is actually okay for them being not available, not on the same page, as long as they didn't do anything positively incorrect. And then we looked at the state checker, which checks this not doing positively incorrect thing. In particular, that a replica cannot backtrack on its head-op. If a replica gave prepare OK for a particular op, it should always remember this op. And that whenever replicas commit, they actually properly advance commit to the same checksum. Which, I mean, okay, maybe I'm blind, but I think that crucial check was actually missing, so we made a pull request of it. Thanks for watching, and see you next week at the usual place, usual time, 5 p.m. UTC, whenever you are on a planet Earth, or maybe even in space, who knows. Goodbye.